Welcome back to our ongoing deep dive into the OEIS.
It's exciting to be back.
Today, we're going to be looking at sequence A00092.
Oh, classic.
Submitted by the founder of the OEIS himself, Neil Sloan.
It's a good one.
And this sequence, it kind of takes us into some really fascinating territory.
Yeah.
Where straightforward estimations, they kind of go hilariously wrong.
They really do.
It's all about counting integer points.
Okay.
Within a sphere, but...
with a twist.
With a twist.
Yeah. What's really cool about A00092 is that it's not just a list of these integer points.
Yeah.
It's a record breaker.
Okay.
It tracks specific sphere sizes where our usual volume-based estimations are the furthest off from the actual count.
Okay. I'm with you so far, but let's unpack that a little bit.
Sure.
So imagine a sphere.
Okay.
And we want to know how many points inside have coordinates that are all whole numbers.
All right.
Like 1, 2, 3, or -507.
Exactly. Yeah.
We're not talking about any point within the sphere, just the ones with, perfect whole number coordinates.
Exactly. And it's tempting to just calculate the sphere's volume and assume that gives us a good estimate of how many of those integer points fit inside.
Yeah.
But A0000092 pinpoints those specific sphere sizes where that estimation goes spectacularly wrong.
It's like we're trying to build a perfectly smooth sphere using only these blocky whole number building blocks.
I like that. That's a great way to visualize it.
And sometimes the fit is surprisingly off.
Yeah, and this sequence highlights a fundamental tension between discrete mathematics, which deals with individual countable objects, and continuous mathematics, the realm of smooth curves and volumes.
So it's kind of like trying to build a perfect circle using only square blocks, right?
Yeah.
You can get close, but there are always going to be some gaps and overlaps.
Precisely. And that brings us to the definitions of A of n, V of n, and P of n.
Right. Those are mentioned in the OEIS entry.
Yes. So let's imagine our sphere is centered at the origin, 0, 0, 0.
Okay.
A of n represents the actual count of those building blocks, those integer points that fall within a sphere of a given size, n.
Got it. So A of n is like painstakingly counting each individual block within our sphere.
Yes.
Okay, what about V of n?
V of n is our volume estimation.
Okay.
It's calculated using the classic formula for the volume of a sphere.
4/3 pi r cubed, yeah.
Exactly. And n, in this case, represents the radius squared.
Okay.
So we're plugging that into the formula to get our estimated volume.
Right, so we have our precise block count, A of n.
Yes.
And our volume estimate, V of n.
Right.
And that's where P of n comes in.
Exactly. P of n is simply the difference between A of n and V of n.
Okay.
A of n minus V of n equals P of n.
Gotcha.
The bigger the absolute value of P of n, the more our volume estimation misses the mark.
So A00092 is highlighting those sphere sizes, those values of n, where P of n hits those record highs.
Yes.
Those moments where our neat and tidy volume estimations are furthest off from the real blocky count.
That's right. And this isn't just some mathematical curiosity. It has real implications for how we understand the relationship between continuous and discrete mathematics.
And this is where it gets really interesting.
Yes.
There's a 1965 paper by Bleicher and Knob from the National Institute of Standards and Technology, NIST.
Okay, I know that one.
And they dive into the nitty-gritty math behind this.
What's fascinating about their work is they explore something called the remainder term.
Okay.
Basically a way to quantify that offness between the block count and the volume estimation in a more general way.
Okay.
A0000092 gives us specific concrete examples where that remainder term becomes unexpectedly large.
So it's like A0000092 is providing a testing ground for these broader mathematical theories.
Precisely. It's a bridge between the theoretical and the practical.
Yeah.
Offering real-world data points to challenge and refine our mathematical models.
That's pretty amazing.
Yeah.
But let's zoom back in on the sequence itself for a moment.
Right.
The first few terms are 1, 2, 5, 6, 14.
Right.
What makes these sphere sizes so special?
That's a great question.
Why are they the record breakers?
That's where things get really intriguing.
Okay.
The answer lies in the complex interplay between number theory and geometry.
All right, well, we'll save that deep dive for a little bit later in the episode.
Sounds good.
All right, so we've seen how a 0000092 kind of highlights where our volume estimations go wrong.
We have.
But, some of our listeners might be wondering, why should a STEM professional care about counting points in a sphere?
Right.
It seems pretty abstract.
Yeah, it might seem that way at first glance, but A0000092 actually points to a broader challenge.
Okay.
In STEM fields,
All right.
using continuous models to represent things that are fundamentally discrete.
Okay.
Think of it like
I'm following you.
trying to represent a smooth curve on a computer screen.
Right.
You can only use pixels, which are individual discrete units.
So no matter how good your computer graphics are, that curve is always going to be a little bit jagged.
That's right.
Because of those pixels.
Exactly.
Yeah.
And in fields like computer graphics, understanding where that pixelated representation deviates the most from the true curve is essential for creating realistic images and animations.
Okay.
A0000092, even though it's about spheres, speaks to that same challenge.
So it's a reminder that our models, while useful, they have limitations.
You do.
We need to be aware of those limitations.
Absolutely.
And know when they might lead us astray.
Absolutely. And the implications go beyond computer graphics.
Okay.
Think about cryptography, where the security of our online communications depends on the difficulty of factoring very large numbers. That's a very discrete problem.
So even though A0000092 itself isn't about cryptography, it points to a branch of mathematics that underpins a lot of our digital world.
It does.
Number theory.
Yeah.
Which explores the properties of integers.
Yeah.
It's crucial for developing secure encryption algorithms.
Exactly. And beyond specific applications, A0000092 encourages a mindset that's valuable in any STEM field.
Like what?
Attention to detail, questioning assumptions, and being comfortable with uncertainty.
So it's about recognizing that our intuition can sometimes be wrong.
Yeah.
And that the most interesting discoveries often come from those moments where our expectations are challenged.
Speaking of challenging expectations, we talked about how A0000092 points out where our volume estimates go wrong.
Right.
But how do we even calculate the exact number of integer points within a sphere?
Yeah, that seems pretty tricky.
It is, yeah.
Counting those building blocks one by one, it seems like it would take forever.
Yeah, especially as the spheres get larger.
Right.
Fortunately, mathematicians have developed clever algorithms and computational tools to tackle this problem.
Okay.
And that's where those Mathematica and ParaGP code snippets in the OEIS entry come in.
Oh, so those snippets aren't just random code.
No.
They're actual tools for calculating A of n efficiently.
That's right.
Okay.
They demonstrate how computation and theoretical mathematics go hand in hand in exploring these kinds of problems.
It's like having a powerful telescope to observe the stars.
I like that.
You know, it lets us see things we could never see with the naked eye.
That's a great analogy. And the fact that those code snippets are included in the OEIS entry speaks to the collaborative spirit of the mathematical community.
Yeah.
People are sharing their tools and knowledge to push the boundaries of what we know.
It's pretty inspiring to think about this global network of math enthusiasts, you know, all working together to explore the vast and often surprising world of numbers.
It is. And A0000092 is a perfect example of how even seemingly simple questions about integers can lead us down fascinating and unexpected paths.
So we've seen how A0000092 has connections to fields like computer science and cryptography.
We have.
But it also raises some bigger questions about mathematics itself. Questions about the nature of estimation.
Right.
The interplay between the continuous and the discrete, and the limitations of our models.
Yeah, those are big questions.
We'll explore those ideas further in the final part of our deep dive. Welcome back to the deep dive.
Glad to be here.
We spent this episode exploring sequence A0000092.
Yeah.
A list of numbers from the OEIS that highlights those sphere sizes where our volume-based estimations are furthest off from the actual count of integer points.
Fascinating stuff.
It's been quite a journey uncovering how this seemingly abstract concept connects to some big ideas in math and even in different STEM fields.
It has been a fascinating exploration. We've seen how A0000092 highlights the limitations of using continuous models to represent discrete phenomena, a challenge that pops up in fields like computer graphics, cryptography, and more.
It's a good reminder that while mathematical models are incredibly powerful tools, they're ultimately simplifications of reality.
They are.
And sometimes, you know, those simplifications lead to some unexpected results.
Exactly. And those unexpected results, like the discrepancies highlighted by A00092, are often the most valuable.
Okay.
They force us to question our assumptions and to look for deeper patterns and explanations.
It's like those moments in science when an experiment doesn't go as planned.
I like that.
Sometimes those failures lead to the most groundbreaking discoveries.
Absolutely. Think about the discovery of penicillin.
Oh, wow.
Or the development of quantum mechanics.
Right.
Those breakthroughs came from observations that didn't fit with existing models, forcing scientists to rethink their understanding of the world.
So in a way, A0000022 embodies that spirit of scientific inquiry.
It does.
It's a reminder to embrace the unexpected.
Yeah.
And to always be questioning, exploring, pushing the boundaries of what we know.
Beautifully put. And for those of you listening who are eager to dive deeper into the world of integer sequences, we highly recommend checking out the OEIS website.
It's an amazing resource.
It is.
It's a treasure trove of mathematical patterns and curiosities.
It is.
Each with its own story to tell.
It's a reminder that the world of math is far from boring.
It really is.
It's a universe filled with unexpected connections, surprising patterns, and endless possibilities for exploration.
It's been a pleasure diving deep with you today.
Likewise.
We hope this episode has sparked your curiosity.
Yeah.
And inspired you to see the world of numbers in a new light.
I think it has.
Until next time, keep exploring, keep questioning,
and
keep diving deep into the fascinating world of mathematics.